Okay, I'm gonna start recording now. Hi, everyone. I know people are going to continue rolling in. Thanks for meeting me online today. I figured this was an option that worked best for everyone who may have traveling and family and all the holiday things to deal with. And it's a bit of a blast from the past. I haven't sat in my dining room and taught biochem for a little while. So I put an announcement out yesterday that basically sort of set the stage for the rest of the semester. We'll have today's online class. We'll also have online lectures during the lab sections next week. So don't come to Science Hall 304 next week. There's no reason to. It's not even a good room to watch a recorded lecture. So we will meet online. I don't care which section you go to. It should be the same material. So I will cover the exact same amount of the lecture slides in the morning session versus the afternoon session. So come to whichever one you want. Arsh, I will fail you. And so, yeah, come to whichever section you want. And they'll both be recorded. So if you really want to hear me say the same thing in a slightly different intonation, feel free to watch both. The final exam information I have basically set up. I've also set up some online and in-person availability for office hours for the coming final exam. Those are a bit subject to change because I've been handed a very large task by my department that is during the last week of classes. And so I will, those are potentially movable. So those details will probably be out today. So with that in mind, I know a lot of you have already started watching the online bioenergetics video. That's great. I think one person has already finished the quiz. So let's get into our material. Okay. And my apologies for not getting the different modules open until yesterday. So I thought I had already done that. So all right. So we are now entering the phase of the class where we take everything that we've learned, right? And we've built this foundation. And so like chapters 1 through 4 were a foundation of how do you make proteins, more or less, right? And the next midterm had what are and how do you make different other biomolecules that are important, right? And then we just finished up with, okay, now that you have these proteins and these biomolecules, what do you do with them, right? How do they interact with each other, and how do enzymes ultimately work? And the reason why I structure it that way rather than going straight from proteins into enzymes and then all that other stuff is that I think it makes more sense to cover the enzyme stuff right before energetics, bioenergetics, and so that you've had this foundation of all the different biomolecules first. And what I want you to take away from this idea is that the biomolecules, all of them, only get made, even if they have a negative delta G, and you could theoretically put them in a beaker of water and walk away and come back and a day, a week, a month, or whatever, and those biomolecules would be around. They only really get made at the time scales and at the concentrations because enzymes exist. What this chapter is going to talk about is how do we evaluate the energetics of those processes, the energetics of enzymes, either breaking bonds or making new ones. All right, and so here we go. Let me move this real quick. So when we talk about metabolism is one of those tricky words because there's sort of colloquial uses and then there's a real biochemistry terminology. Metabolism, when it comes to biochemistry, is really moving energy around. Okay, what we're generally going to do as organisms is take in big molecules break them down, extract energy from those processes, and use that energy to make small molecules into big molecules that we need in the time and place that we need them. Okay, so generally speaking, this is a bidirectional process. Catabolism is breaking down big things into small things, extracting energy. And by breaking them down into small things, those final products are often very energy depleted, like fully oxidized carbons, for example, fully reduced oxygens, and some ammonia, basically. And in the process, we're stripping off energy. We're synthesizing ATP. We're reducing a number of electron carriers. Okay, we use that energy to take the small molecules that we learned about, all those monomeric units, the amino acids, sugars, fatty acids, nucleotides, and we make big stuff. Right, and the completely zoomed out energetics of this process is big things becoming lots of small things is a massive increase in entropy. So therefore, there's a big negative delta G for take random carbohydrate or random fat, random protein, and break it into constituent components, or all the way down into fully oxidized carbons, for example. Like big negative delta G for that. A lot of that you're going to lose to just entropy in the environment, right? But if you can capture as much of it as possible, that energy can be transferred to making macromolecules from cellular precursors. So we need a bunch of energy all the time. And part of that is macromolecular synthesis, make big things out of small things, construct proteins and nucleic acids from their precursors, construct complex lipids from their simpler precursors, and so forth. Always fighting against entropy. But there's other things that we need the energy for. We need transport. Okay, so this includes like moving oxygen around your body, right? You're transporting oxygen, it binds to hemoglobin in your lungs, and that hemoglobin releases the oxygen in your peripheral tissues. Well, that doesn't happen without a bunch of energy, right? Your heart's got to be pumping that blood around. Your lungs have to be to fill and empty based upon the movement of your diaphragm muscles, right, and so on, right? You have cells that are constantly keeping your lung tissue wet, and so synthesizing the mucus that allows you to breathe takes energy, all that stuff, right? And we've already talked about motion, like actin, myosin contractions, but this happens at a smaller level too. Cells moving around don't necessarily use actin and myosin, but may use other dynamic processes, and moving things around inside of a cell too, right? You synthesize something in one part of a cell and then move it to another part of a cell. If you're not letting just random diffusion happen and you actually need to direct that, that takes energy. So again, we've mentioned before that enzymes have limited tool sets, right? There's 6 classes of enzymes, 3 main ways that they work, right? And that is true for breakdown as well as creation of bonds, right? So we have our 6 examples of reactions down here. Here are the 3 classes: acid-base catalysis, covalent catalysis, metal ion catalysis. And there are example reactions at the end of this slide deck, which we probably won't go over in too much detail. But when we consider the breakdown of a carbon-carbon bond or a carbon-hydrogen bond, a covalent bond, right? The types of things that we're going to worry about as we say metabolizing something we've eaten. When we break that bond represents shared electrons between 2 atoms, right? That line means that this carbon and this hydrogen are sharing a pair of electrons. You've seen carbon on its own and hydrogen on its own. You know that hydrogen on its own has 1 electron, and carbon on its own has on its outer shell 4 electrons, right? That's why carbon can make these 4 bonds, hydrogen can make the 1, right? So the single electron of hydrogen and one of those 4 outer valence electrons for carbon come together, share this the shared orbital here, right? Well, so if you break that bond, there's two ways you can basically do it. You can split the electrons evenly, so they go back to their individual atoms more or less, or you can split it unevenly, right? Homolytic would be an even split, but that's going to produce radicals, right? Single electrons. Those single electrons, that's dangerous, right? Because if you know anything about how radicals react with stuff, it's that they react with all the stuff all the time. And they create chain reactions where a radical reacting with something, it basically produces a radical product. So it never ends until something can absorb that radical. So this is where antioxidant compounds, like vitamin E, for example, they get their name because they can actually stop these chain reaction processes by absorbing these extra electrons. Okay, so this same deal happens if you break a carbon-carbon bond versus a carbon-hydrogen bond. If you have homolytic cleavage, you're going to end up with single electron radicals. All right, heterolytic cleavage means that the electrons are going to go to one side or the other, right? And if it's a carbon hydrogen, you could end up with a carbanion or carbocation, a proton or a hydride, right? If it's carbon-carbon, carbanions, carbocations. And you know from Orgo, right, that some of these are more stable than others, depending on the environment, right? We've seen protons all the time. They're pretty stable in water, right? So this is probably generally favored in depending on the pH of the environment, right? Hydrides are going to have a different reactivity, for example. You know that carbanions or carbocations are not the sort of thing that would just float around in aqueous solution for very long, right? So when we think about how an enzyme's working, where they're going to be breaking some of these bonds, right? They need to stabilize these things, so they probably represent the transition state. So all the stuff that we're going to talk about today is going to be constrained by what we know are the laws of thermodynamics, right? The first law of thermodynamics is that energy cannot be created or destroyed. That means no matter what, if there's a negative delta G for something, that means there must be some positive delta G somewhere else, right? The universe ends up balancing it all out, right? But that energy will generally shift towards entropy, right? So there's always going to end up being a little bit of extra disorder at the end of the entire process. Okay, so now with that in mind, this is a classic question. Biological systems are highly ordered, right? We are made up of big proteins and big biomolecules that all must have much lower entropy than the types of small molecule precursors, right? Because we've basically glued them all together, so they each have lower entropy. So why do we not violate the second law of thermodynamics? This is actually a classic question that, like, creationists and science deniers and stuff like that often will use to, like, try to fool people, right? Well, the laws of thermodynamics say that, we shouldn't exist, right? Well, we do, obviously. Does anybody know the answer to this? We catabolize larger molecules, which creates more entropy, right? Well, that's part of it. Anybody else have an idea? All right, I'll give you the answer. Yeah, there we go. Jules got it. We're not a closed system. These laws apply specifically, the energy created and destroyed, closed systems. They apply to closed systems, which means if there's no external input or output of energy, you can't just create new energy within that system. The Earth is not a closed system. We are constantly getting energy from an external source, the sun. Not to mention some other processes, if you really care about life at the sea vent, the thermal vents at the bottom of the ocean, right? But the vast majority of the external energy coming and hitting the Earth is from the sun. So while the universe may not be creating or destroying more energy, the net movement of energy to planet Earth means that we can do some stuff that on a surface level might violate the second law of thermodynamics. Okay. So the entropy of the universe increases as biology gains order, and we're not closed systems. We're constantly intaking energy. So this is where Arsh is right. We're constantly intaking energy. You probably had some breakfast, or you will have some lunch soon, right? That's an intake of energy. And you can use that, you can catabolize those things, extract the energy to build stuff, right? So that means we're not a closed system because we're constantly inputting energy. The Earth is not a closed system because it's constantly inputting energy. But we need to keep these things in mind as we move forward, right? We're going to be slaves to the Gibbs law, right? This equation dictates everything. Delta G equals delta H minus T delta S, right? So the free energy of a system depends upon what bonds you're breaking and creating, and are you increasing or decreasing the entropy of the measured system, okay? As a general rule, because this is a collection of all the bonds you're making and breaking. As a general rule, if you end up with a net gain of stable bonds, right? Maybe you take one bond that's a little less stable and create a new bond that's more stable, right? A net gain of more stable bonds is a negative delta H. A net breakage of bonds is a positive delta H, okay? The entropy side, a net breakage of bonds is probably a positive delta S, right? So sometimes these things are going in opposite directions. You have to be mindful of enthalpic and entropic effects. And this is where the temperature dependence of systems really matters, right? What is favorable at one temperature can become unfavorable at a lower temperature or a higher temperature. It really depends on what the balance is. So overall, delta H is your change in enthalpy, and your enthalpy will be a positive delta H for all bond breakage and a negative delta H for all bond formation. So the net is if you trade weaker bonds for stronger bonds overall. For entropy, positive delta S is more molecular freedom, and that molecular freedom can be a little esoteric or difficult to sort of imagine, but it's all the degrees of rotation that you can possibly have, right? If you're a single small molecule floating around in aqueous solution, you can tumble in all these different directions, you can stretch and rotate around, single bonds, and you can interact with lots of different things. Constrain any of those things, right? Constrain, just molecular rotation, right? Trade a single bond for a double bond. Double bonds, you can't rotate around that bond, right? So that can actually constrain the entropy of a molecule, right? If you take your molecule from one solvent and put it in a different solvent, the types of interactions it can have with the solvent can change, and that can actually affect the entropy. Right? So think about the entropic effects of fats in water. The reason the fats all come together is because the solvent is driving the energetics of the system. If you end up with more randomness, you have a positive delta S, so the minus T delta S ends up being negative. And we talked about standard free energy in the last lecture of the enzymes. And I want to make sure that you know or really understand that biochemical standard free energy uses some of the same rules. So we're going to use room temperature. We're going to use 1 atmosphere pressure, or 1 megapascal if you prefer. And everything in the reaction is at 1 molar concentration, except for water and protons and magnesium. Okay, we're going to add in the magnesium because a lot of stuff's going to need ATP. Okay, so everything else is the same, and we're just going to change, rather than just using the degree sign, we're going to actually use a little prime as well to indicate this is biochemical free energy chain. Okay, this is important to really appreciate that biochemical standard free energy change means that we can take any particular reaction, standardize the conditions, figure out the energetics of that. And importantly, then we can say, well, this is not what the conditions are in this given cell at this given time. So how do the conditions change, and what does that change for the energetics? So when we have our standard free energy of a system, we can also then take this delta G, and we've already seen that we can relate that to an equilibrium of that reaction. Under standard conditions, if you started with molecules A and B that can interconvert to molecules C and D, and there could be different molar ratios of these different molecules, right? If you were under standard free energy conditions, everything would have to start at 1 molar concentration, right? So 1 molar A plus 1 molar B, let's just assume for simplicity, it's 1 molecule of A reacts with 1 molecule of B. So lowercase a, lowercase b, c, and d are all 1, right? A plus B equals C plus D, right? As a reversible reaction. That would have to be 1 molar concentration of each of A, B, C, and D. And the equilibrium of that reaction would represent the ratios of products over reactants, right? If you needed 2 A's and 1 B to create 1 C and 1 D or something, then you would add these exponents in, okay? But the idea here is at equilibrium, you clearly don't have 1 molar concentration of each of these, right? So what we're doing is, under standard conditions, we're setting up one set of the system. Like, here's like an imaginary initial value or initial state of the system of this particular reaction. And there's 1 molar concentration of all of them, and it's at room temperature, and so on. If you let it relax and it goes all the way to equilibrium, and that could take seconds, minutes, days, millennia, right? Your final concentrations would be represented here. So the KEQ, or the equilibrium constant, and with the prime there telling you biochemical standard conditions, that result will depend upon this delta G. So if you have a negative delta G under these standard conditions, we would call that a spontaneous reaction, right? So that would mean it would go forward. It would drive towards product creation. So we would expect to end up with more C and D in comparison to A and B. We would expect to end up with more products over reactants. This fraction would then be a larger number over a smaller number, and a KEQ would be some value more than 1 if you had a negative delta G. If you had a positive delta G, the reaction would occur in the other direction, right? C and D would have a net conversion into A and B. You'd have less C and D, more A and B. You'd have a fraction that's less than 1. KEQ can never be it can never be a negative number or anything. It's a fraction that is either more than 1 or less than 1. And that's going to rate, sorry, that KEQ is going to be dependent upon what is the forward rate of the reaction and the backward rate of the reaction. And if you recall, those reaction rate equations that we, excuse me, that we covered in lecture, and it showed up on the midterm, right? Those were basically how we would define how K interacts with how much A and B and C and D you've got to drive the forward and backward rate. And then at equilibrium, the backward rate and the forward rate are the same. So we can directly interrelate these things. Delta G under standard conditions, right, directly relates to the log, the natural log of KEQ. But notice this minus sign, right? We can convert this a little bit, right? So if this is a natural log, you basically take everything to the e to the power of, and you can say delta G, this number here is going to relate to KEQ. So there's an inverse correlation between delta G and KEQ, right? The more, if this is negative at all, this is a number greater than 1. That's basically how it works, right? So what you see here is if KEQ equals 1, that would suggest your products and your reactants are the same concentration. So that means the initial conditions we set up here are the final conditions at equilibrium. Nothing happened. It was already at equilibrium. KEQ equals 1, that's the same as delta G equals 0. Equilibrium under standard conditions, right? KEQ, some number greater than 1, that would be a fraction favoring the numerator, negative delta G. KEQ smaller than 1, a fraction favoring the denominator, right? That would be a positive delta G under standard conditions, right? So this is what that's telling you. So let's look at some examples. This is the standard free energy change of some chemical reactions. Some of these you will get very familiar with because we will be describing how these reactions actually occur. Okay, we will look into the actual systems of ATP hydrolysis and phosphorylation of glucose and so on. Okay, so what you see here is the delta G's of these different reactions, kilojoules per mole and kilocalories per mole. I've just made the general choice of working with kilojoules per mole over the course of this class, but they're just a simple interconversion. This is always negative if this is negative and vice versa. Okay, just make sure you keep your units straight. All right, so let's look at this. What is, under standard conditions, the delta G of not ATP hydrolysis, which is what's represented here, ATP plus H2O creating ADP plus inorganic phosphate, right? So adenosine triphosphate, adenosine diphosphate. You are hydrolyzing the gamma phosphate, the terminal phosphate, producing an adenosine diphosphate and the free phosphate. So what is the standard delta G of making or synthesizing new ATP from ADP and phosphate? Somebody throw that in chat. Kilojoules per mole, please. I'll just sit here and drink coffee until somebody puts it in the chat. I could play the Jeopardy theme if you want. What's the delta G of the synthesis of ATP? Right, exactly. Plus 30.5 kilojoules per mole. Might have seemed like a trick question, right? For all of these, this is showing the reaction going in one direction. The reverse reaction has to be exactly the same magnitude of a delta G change. You just flip in the sign. That's all. So as we continue through the processes here, right, if you see a unidirectional measure of the delta G of a particular reaction under standard conditions, know that the opposite reaction is just the opposite sign, but the same magnitude. So in this case, the delta G of glucose 6-phosphate being the synthesis of glucose 6-phosphate from glucose and inorganic phosphate, right? This would be the reverse of that, right? So it's a positive 13.8. Right, so we're going from glucose plus inorganic phosphate. So what then if you took ATP and water and glucose and inorganic phosphate and you produced ADP plus inorganic phosphate plus glucose 6-phosphate plus H2O, right? So first of all, what we can do here is figure out what's on both sides of the reaction, right? We can cancel out this inorganic phosphate, right? We can cancel out this water, right? It's on both sides of the arrows. So net, we're going to take glucose and ATP and produce glucose 6-phosphate and ADP. So what is the overall delta G? Well, so what we've done, right, is we've taken ATP and hydrolyzed it to ADP. So we're going to take that negative 30, and forgive me, I'm not using a pen this time. This is me using a mouse, which is not ideal, right? And then this glucose into glucose 6-phosphate, we established was plus 13.8. All right, and so you can do the math here, but this is a negative number, right? Oops. So that was 13.5, it'd be 17, so 16.7, yeah. All right, so overall, under standard conditions, the phosphorylation of glucose using ATP has a negative 16.7 kilojoule per mole delta G, right? This is stuff you've done before, right? Just trying to refresh your memory on basically how to balance these equations and think thoughtfully about reactions, okay? So we would say that under standard conditions, you had a 1 molar concentration of ATP and a 1 molar concentration of glucose, right? And you started with a 1 molar concentration of ADP and glucose 6-phosphate, and you let it sit, you would continue to make more glucose 6-phosphate and more ADP, and you would continue to phosphorylate glucose until you reached a new equilibrium that would favor those products even more. All right, so another key idea here is that that's standard conditions. So that tells you, given this temperature and pressure and these concentrations, where would you expect a reaction to go if you let it, right? KEQ with that little prime is telling you where it would go under standard conditions from starting at those standard conditions. So if you considered some molecule X that could convert to some molecule Y, right? This could just be, some sort of isomerization. It could be, like it protonates or deprotonates, whatever, like all these sorts of things. Like it could be any number of them, right? But simple, X can interconvert into Y. It's reversible. If KEQ of X to Y is less than 1, that would mean the delta G under standard conditions of that interconversion would be greater than 0, right? And so what would that look like in terms of an X to Y equilibrium? Well, if you started at 1 molar X, 1 molar Y, but you have a positive delta G under standard conditions, you should expect creation of more X, right? The backwards reaction, Y to X, would have a negative delta G under standard conditions. So you would expect more X and less Y at equilibrium. But now let's take things out of standard conditions. what if you had a beaker and there's only Y in it? Well, you would imagine if there was only Y in it and you let it go to equilibrium, you would end up with the exact same ratio than if you started at 1 molar, 1 molar. You're just starting with less stuff in this case, right? I could have put 2 molar here, and you would still end up with the same ratio of X to Y at equilibrium because the energetics of the system have not changed. You're just out of equilibrium. Most of the time, standard conditions means the system is out of equilibrium unless that delta G is under standard conditions is 0, right? So at equilibrium, you would still end up in the same place. And so this is a key idea. You're always going to be moving towards equilibrium. Systems never move away from equilibrium. So how far you are from equilibrium is basically a measure of the energy of the system. It's the potential energy of the system. It's kind of like, if you can prime certain, physical things. Like the higher you hold a rock, right, the more force it'll actually exert when it drops. Like when it hits, than if it had it, 5 centimeters above a table versus 1 meter, the amount of acceleration and the force is different, right? A rock sitting on the table is essentially at equilibrium and has no force. So you get more force the further you are from equilibrium. That means your delta G, not delta G under standard conditions, will be greater or smaller depending on how far from equilibrium you are. The other thing is our reactions are linked typically to other stuff. Very few things in the cell are just X interconverting into Y, right? Often things are part of chains of reactions. And so X could be converted into Y, but it's very likely that Y gets also converted into Z. And maybe X into Y is unfavorable, generally speaking, but Y into Z might be really favorable. And so if that's the case, for every X that becomes a Y, that Y is more likely to become a Z, and now you have less Y, and so more X can become Y. So this is what we would call sequestering products. We're driving an unfavorable reaction, X to Y, forward because a favorable reaction, Y to Z, is happening downstream and they're linked. This is how cells are able to make things like giant proteins and DNA molecules, which are individually, adding one more chunk to an amino acid chain or to a chain of nucleic acids, right, is energetically unfavorable. But you can make all that stuff because the next reaction is favorable. So we can actually use these systems, right, under standard free energy. We know basically what does the system look like if it goes to equilibrium, and under these conditions, how far from equilibrium you are. Then we can ask, okay, what is the system at now? Are you closer to equilibrium or are you further from equilibrium? And that's basically what this equation is. And we'll go through all the little bits in a little bit over a couple of slides here, okay? So first of all, the standard free energy change of a particular reaction, and using our model of X converting into Y, and that's probably a positive, unfavorable reaction, Y converted into Z, which is a negative, favorable reaction, right? The overall X to Z conversion is simply a summation of these two delta Gs, right? And so this is a small positive and a big negative. It's a small negative overall, right here. I will graphically write that. So like, okay, this is a, oops. There we go, that's what I wanted. Small positive and big negative, that's what that is. So the overall effect of a small positive and big negative is a small negative. And let me use the eraser there. Okay. So if I, just to highlight it a little bit more, so that's a small positive and a big negative. There we go. How about that? And we end up with a small negative summation of a standard free energy. So for this particular reaction, the standard free energy of X to Z would have, say, a small negative number. Okay. The next part is, what is the current conditions? So KEQ would relate directly to standard delta G. Current conditions asks, what is the system right now? Okay, and it's the same idea. It's KEQ, but not standard conditions, it's current conditions. It's the product of the concentrations of the products over the concentrations of reactants. So are you closer or further from equilibrium? And generally speaking, if you compare KEQ to Q, if Q is a larger number than K, that means Q has more products than you would expect at equilibrium and fewer reactants than you would expect at equilibrium. So you are further from equilibrium towards the product side. You've overshot equilibrium. You have too many products. If KEQ is smaller, or sorry, if Q is smaller than KEQ, right? If Q ends up smaller than KEQ, that means there are an overabundance of reactants compared to products than what you would expect at equilibrium. So this part is asking you, how far away from equilibrium are you? And then there's a temperature dependence here, because that matters. If you're, the further you are from equilibrium, and depending on what the temperature is, I can shift how your delta G of the overall reaction is. And I want to help emphasize here, right? Because we're using delta G in this equation, and then we're using basically the current system reaction quotient. That's what Q is, the reaction quotient. It would be useful to compare directly to KEQ, I think, right? So in this form, we've converted delta G into that KEQ form. So the current delta G of a system is, what would you expect at equilibrium compared to what we are now? There we go. That's it. So the delta G of a reaction is like standard, not standard delta G, but the delta G of a reaction is just asking how far out of equilibrium you are. And the further out of equilibrium you are, the larger the magnitude delta G is going to have. Does this make sense to everyone? Does anybody have a question about this kind of a general idea? So the underlying principle here that you can hopefully see is that the further from equilibrium you are, the more energy you can get out of a system. It's kind of like the more you wound up a toy, or the more you've compressed a spring, or all the possible things that you can imagine. It's basically more potential energy in the system, and therefore a bigger driving force. So let's put that in terms of ATP, which is the major cellular source of that free energy driving these reactions, right? So here is ATP's structure down here in the bottom right. I have a quibble with this structure, right? Because it's not showing this molecule at physiological pH, is it? You should expect that this will deprotonate, and this will deprotonate, and this will deprotonate, and this will deprotonate. So in fact, you'll have 4 minus charges in relatively close proximity to each other, right? You can see also this is ATP and not DATP, right? Because the 2' phosphate, or sorry, the 2' hydroxyl is present, and it's not a hydrogen, right? So it's not DATP. For ATP, these 2 phosphates, this is the alpha, this is the beta, and this is the gamma phosphate, that are, I always screw that up. So the alpha, beta, and gamma phosphates, here we go. They're attached via phosphodiester bonds. And if you break this bond right here, or alternatively this bond right here, there's actually a big negative delta G under standard conditions associated with that. And that's, of course, catalyzed by enzyme. Even though it has a big negative delta G, you want it to be catalyzed by enzymes, because if it just does on its own, it's wasted stored energy. So how does that happen? Well, for the chem majors in particular, it might be nice to know that there typically is an SN2 mechanism, that the nucleophile is typically some component of a protein or other biological molecule that will gain the phosphate. And there are cases where ATP donates what's called a pyrophosphate, so PPI. So it's the 2 phosphates that are bound by an ester bond. But most of the time, we're going to see ATP hydrolyzed into ADP. And it's often a multi-step reaction where the phosphate is stuck to something and then it's released. You might recall when we were talking about the enzymes working in different mechanisms, right? That there's sometimes a ping pong mechanism in which an enzyme binds substrate 1 and product 1 leaves, but the enzyme is now changed, and then binds substrate 2, produces product 2, and the enzyme goes back to its original state. That's what happens a lot of times with protein kinases. Protein kinases will maybe phosphorylate themselves and then transfer that phosphate to their final product, for example. All right, so hydrolysis of ATP is highly favorable under standard conditions. So why? This is kind of a key idea. There are multiple routes to negative delta Gs here. First of all, you have all these negative charges in close proximity. So you have charge-charge repulsion within the same molecule. If you cleave off that gamma phosphate, that terminal phosphate, you still have a bunch of charges, negative charges in close proximity, but you've relieved some of the charge-charge distribution. So you have better charge separation. We're also going from 1 molecule to 2, right? ADP plus inorganic phosphate. So that's an increase in entropy overall. And here's the subtle one that you might not appreciate, but is actually a really big deal, is that free phosphate, that phosphate that's been cleaved off, actually will deprotonate. So there's actually a little bit, you get a little extra bonus there, because the deprotonation produces basically a proton as another product, right? But the key thing is now, when that's gone, it's an O- here. But that leaves, so I'm going to draw here, right? So if this goes away, you end up with an O- here. And now you have 3 O- and a phosphate, and there's 5 net bonds. And what you end up seeing is that all of these phosphate to oxygen bonds end up being identical. And you actually have a resonance stability where each of these phosphorus to oxygen bonds have a partial double bond characteristic, and they distribute the 3 negative charges across the 4 oxygens. So they each one ends up being partially negatively charged. on average, right? So in a way, you can think about this as releasing this phosphate actually produces a whole bunch of different products, lots and lots of different extra products, and that are extra stable. So super stable products, because of resonance stability, and we'll see tautomerization later on as well as another example, that's also really key. So you're going to have the entropy gain. That one would have hopefully been a little obvious. Better charge separation, like take those negative charges away from each other, so not repelling each other in the same molecule, better, right? And then super stable final products. All of that adds to a big negative delta G under standard conditions. Okay? Cells are not under standard conditions. You do not have 1 molar concentration of ATP and of ADP and of inorganic phosphate and so on, right? So this is one of the things that if you have already watched the lecture, the video lecture, delta GP is discussed in there a little bit, certainly in the readings, but this is the free energy specifically of the phosphorylation or dephosphorylation of ATP, the dephosphorylation of ATP. So in the cell, free ATP, free ADP, and free inorganic phosphate are actually under lots of different controls. And the total concentrations of each of these substantially differ from free concentrations. That matters. Free concentrations are what will be used in your Q, right, in your reaction quotient. There are lots of ways that we can sequester inorganic phosphate, for example. So if our reaction is ATP getting hydrolyzed to produce ADP and inorganic phosphate, and we'll just ignore the water and the proton, for example, if every time you sequester away an inorganic phosphate, that drops your concentration of products. Therefore, the forward reaction becomes a little more favorable, right? If you sequester away or reduce your ADP concentrations, that would make your forward reaction more more favorable. If you increase your ATP concentrations, make forward reaction more favorable. Okay, so under cellular conditions, what are our relative concentrations of these things? So this table is great because it shows you a variety of different cell types, lots of different eukaryotic mammalian cell types. So like hepatocytes, these are liver cells. Myocytes, your liver or muscle cells, neurons, and erythrocytes, these are red blood cells, right? And you can see measured amounts of ATP, ADP, adenosine monophosphate, which is also involved in some of these reactions, but we're going to ignore for our initial consideration here. Inorganic phosphate, and then phosphocreatine, which we'll talk about in a little bit, okay? So you can see that under standard conditions, you just grab some red blood cells or rat liver cells or whatever, you see that there's a lot more ATP than there is ADP, right? So the balance of this reactant, ATP, versus this product is shifted. Free phosphate can vary quite a bit, and we'll talk about some strategies about that. Phosphocreatine, and if you've heard of creatine before, it's probably mostly because it's a dietary supplement that you can, buy, and bodybuilders and people that work out a lot often swear by it. But its role in the cell is to be a reservoir for phosphates, and you find it at high levels in muscle cells and in neurons because when there's an abundance of phosphates available, and when there's abundance of ATP available, it's favorable to create phosphocreatine. But then if something happens, you have to run away from a lion on the Serengeti or something, right? You might deplete your ATP relatively rapidly and suddenly becomes favorable for phosphocreatine to phosphorylate ADP and create new ATP. Okay, so if we actually use these numbers and kind of calculate what is our delta G, we can totally figure this out. Okay, so what is the delta G of ATP hydrolysis in rat hepatocytes at body temperature? Actually, this is at human body temperature. Rats have a slightly higher one, but we're gonna run with 37. Okay, so delta GP is going to equal the standard delta G of ATP hydrolysis, and then we're going to use our concentrations of ADP, inorganic phosphate, and ATP at 37 degrees here to figure out how far away from that equilibrium are we. Okay, so here's our standard hydrolysis, RT. So R and T, 310 will be our stand-in for 37 degrees Celsius. Key detail here. Notice I've converted all of these concentrations into molar. Okay, they're millimolar up here. And this is important. This is not really all that important if you have one concentration over one concentration. But if you're multiplying a couple of concentrations together, you better do this. Otherwise, you're going to end up with the wrong values. Okay, so it's always best to convert to molar, do your math, and then convert back into useful units like millimolar. So in this case, ADP and inorganic phosphate concentrations multiplied together over ATP. Right, what you see is our total is negative 46.7. So standard conditions. So what that means is if this was negative 30.5, right, that must mean this was negative 16.2 kilojoules per mole. Under standard conditions, ATP hydrolysis is favorable. Under cellular conditions, it's even more favorable because you're even further away from equilibrium. And so ATP hydrolysis in cells ends up being super awesome. Super big negative delta G, you can do a lot of work with it. You could do the same thing for, say, muscle cells and compare these concentrations and so on and see if delta GP is different in these different tissues. Or maybe instead of eukaryotes, look at a prokaryote like E. coli, where everything has to be in the same cell. All right. Another thing, and I mentioned this about ATP, is that the processes by which it's used, right, to hydrolyze that terminal phosphate provides a lot of energy. But you can't just take an ATP molecule and put it next to something else, hydrolyze that phosphate, and expect something to happen. In order for the energy released for ATP hydrolysis, it has to be to affect something else. It usually has to be worked into the process. So as on the top here is a one-step reaction where we show how do you make glutamine out of glutamate. Right? You guys remember these. So glutamate and glutamine can be converted into each other. And in the case of glutamate, you take ammonia and ATP, hydrolyze the ATP, and you get yourself some glutamine, right? So this doesn't just like burn next door. It's actually incorporated into the reaction process. Okay, so the first step of this reaction is actually just the enzyme grabs glutamate and ATP. ATP is hydrolyzed and ADP dissociates, but that phosphate is now stuck on the glutamate. So the enzyme is stuck to this glutamate that has a phosphate, right? It's a glutamyl phosphate intermediate. Then NH3 comes along and displaces the phosphate, releasing the inorganic phosphate. So it's actually a two-step reaction, right? This is that ping pong reaction I was kind of talking about. So if we consider our previous slide, go back to this, right? There are three major things, there are three major things that we're looking for how is a reaction favorable? Wouldn't R need to be in kilojoules? Let's see. As long as, so if you multiply this and then, yes, like do the math, making sure you talk about kilojoules versus joules. I'm pretty sure I did that right. I might not have added the extra step of converting. Okay, you can double check my math. Thanks, Jules. But going back to this, right? There's the three things that we want to look at for this ATP hydrolysis energy, right? One is increased entropy, right? So more molecules being released. All right. One is the relief of the charge repulsion. And then finally, the release of the superstable products. Okay. So if we look at this stepwise reaction, what are we doing? On the first one, we're phosphorylating glutamate, essentially. Okay. So are we ending up with a relief of charge repulsion? So yes, so we're getting here, this is going to, I'm gonna forgive my, okay, so this will relieve the negative charge repulsion within the ATP molecule, right? What else do we have to worry about? We also want to see, so that's the better charge separation, resonance products and entropy. Are we getting an entropic gain here? I'm going to say no, because you're taking ATP and converting it into ADP, but the phosphate, the other product, is now covalent bound. So you're not getting the entropic gain. Are you getting a super stable final product? No, because that phosphoryl group bound to the glutamate, so you glutanyl phosphate, this can't have resonance stability because it's covalently bound. So you only get one of the three in that first step, but you still have some gain. In the second step, this is where you get your stable final product. Give me 1 second, guys. There is, oops. I need to go answer the door. All right. Sorry about that. My apologies. Why? Okay. So the second step releases this more stable final product. Right. What was the third one we need to worry about? Entropy. Right. And increased entropy, because we have now this release of the extra product. So this is including, sort of in a stepwise manner, the three different big benefits you get from ATP hydrolysis, but not all at once, right? This is kind of akin to if you wanted to take a piece of paper and burn it, right? You can't hold a match far apart from the paper, you know. Piece of paper, match, can't hold the match over here, right? You need to incorporate the actual flame onto the paper, okay? So incorporating ATP in the reaction where you stepwise move through all the parts that provide that major gain allows for something like this to occur. And we'll see this over and over as we get into other products that we're going to study. This is the last step in glycolysis, which will be one of the things we're going to learn next week. The hydrolysis of phosphoenol pyruvate has a big negative delta G under standard conditions. Here's phosphoenol pyruvate. You hydrolyze, release that phosphate. We already know that hydrolysis releasing a single phosphate is going to end up producing a really nice super stable phosphate product, right? Notice this molecule has some negative charges all in close proximity, right? So we're going to get another relief of charge-charge distribution. We're going to take one molecule and produce two, right? Pyruvate and inorganic phosphate. But then also, since pyruvate can tautomerize between an enol form and a keto form, it's like a super stable final product on its own. So it gets an even bigger negative delta G. And this is the last step in glycolysis. And so what you'll see is that you guys are gonna learn all 10 steps of glycolysis. And some of them are pretty favorable and some of them are unfavorable. But if they're all chained together and the last step is like this big drop, big negative delta G, it kind of drives the whole process, right? Remember that example of X converting into Y, converting into Z. If that last step is really negative in terms of delta G, everything gets a nice boost. We'll also see that when we're moving different functional groups around. So acetyl-CoA, we will use to move acetyl groups. So 2 carbon chains essentially. So the acetyl group is bound to the coenzyme acetyl. That's what the co means for a CoA. It's coenzyme A. You hydrolyze the acetyl group, and you get now your reduced form of the acetyl-CoA. And acetic acid itself is a super stable product because it has resonance stability after ionizing. And so it has a nice big negative delta G. And so moving 2 carbon units around in the cell is favorable using acetyl-CoA, for example. So in general, we're going to find high energy hydrolysis is our strategy for driving reactions. These hydrolysis reactions, they increase entropy because you end up with some gain in the total number of molecules. They reduce bond strain primarily because of electrostatic repulsions. They have super stable products that are super stabilized by ionization, resonance, and tautomerization, some combination of these things, right? So if your final products end up being super stable, that means conversion of stuff upstream can be powered by that final, like, relaxed, low energy system. Okay, so in the cell, ATP is going to be our main driver of these processes. It's not the only driver of it, but ATP is used for so many things at this, all at the same time, right? Not only the powering of reactions, but also, I mean, it's necessary for creation of new RNA, right? So it's constantly in use, constantly in production, and then the hydrolysis is going to lead to increased levels of ADP. So if you are rapidly moving a lot of muscle tissue, right, you're going to use up a lot of ATP. So there are strategies cells have to make it easier to make more ATP. And it's going to use the same sort of ideas, right? Change your ratios of products and reactants, right? Every time you increase the amount of reactants and or decrease the amount of products, you make the reaction more favorable. So we have nucleoside diphosphate kinases, and they will shuffle diphosphates around. So if ATP is what's normally being used for energetic systems, and your cell ends up with like some extra CTP, right? These phosphates can, kinases can grab an ADP and a CTP and move the gamma phosphate from that extra CTP to the ADP and make more ATP. Okay, so you can move things around from all the other things that are triphosphates. Adenylate kinase takes 2 ADPs and moves one of the phosphates, producing ATP and AMP, which is why the AMP concentration showed up in that list. Okay? Creatine, this is where it shows up. Creatine kinase is an enzyme that will take creatine, and if you have a whole bunch of ATP, it phosphorylates phosphocreatine. That is a favorable reaction if you have lots of ATP, but as ATP concentrations drop because you're using your muscles a whole bunch, the reverse reaction becomes favorable. And so creatine kinase will then phosphorylate ADP using this storage of inorganic phosphate. So it basically keeps the concentration of inorganic phosphate a little artificially low. And then polyphosphate kinases will take if you have high levels of ATP, it will take some of those terminal phosphates, those gamma phosphates, and actually link them together. You get these long chains of phosphates. And then when ATP levels are low, the reverse reaction happens, where now you have these long chains of phosphates that can be added to ADP and create new ATP when an emergency arises. All right, so this is usually where I stop. I want you to sort of think about why reactions like ATP hydrolysis end up being favorable, and then why in cellular conditions they're even more favorable. And that's emphasized also in the video quiz lecture. And that's your big takeaway from today. When we talk about this stuff on Monday, we'll focus on redox reactions and just kind of remind you about all that stuff. And then we'll dive into glycolysis on Wednesday. And next Thursday, I will see you. I promise not to lecture during the entire lab period because frankly, that's a lot. And I would have to do it twice. So that sounds terrible. So I'm not going to do it. Everyone, please have a safe and happy Thanksgiving holiday weekend. Please take a little time to enjoy family and a little time off. Don't step completely away from biochemistry if you can, but let's all have a safe and wonderful holiday. Thank you so much for coming today. I will see you on Monday. Oh boy. Yeah, his hair did really change color, didn't it? All right, folks. If anybody has any questions, please reach out. And otherwise, I'll talk to you later.